So in this question here, we've got a period of 10 seconds during calm weather and a period of 3 seconds. So it's going to be part 1 and part 2. Calculate the frequency of each of the waves and then complement on the amplitude and wave energy in each one. Okay, so let's get started here. So this one here has a period of 10 seconds. So period, capital T, is equal to 10 seconds. Frequency is equal to the inverse of the period, which is equal to 1 over 10, which equals 0.1 seconds. Oh, sorry, not 0.1 seconds, 0.1 hertz. For the next one, it's every 3 seconds, so period is equal to 3 seconds. So again, frequency is the inverse of the period, which is going to be 1 over 3, so therefore it's going to be 0.33 recurring hertz. Which makes sense because that should be a higher value than this one because it's occurring more frequently. Comment on the amplitude and the wave energy in each situation. Well, the period and the frequency are not tied to the amplitude because they're separate vectors, so therefore we assume that they're going to be constant. Technically there's not enough information in the question, however there is no relationship between period and frequency regarding the amplitude. They're separate quantities. An electric oscillator, so let's go down to question number 10 here. An oscillator vibrates 10,000 times a second, so 10 to the power of 4. Find out its period. So we're doing the reverse of this question here. So frequency is 10 to the power 4 hertz, and period is equal to the inverse of the frequency. So that's going to be equal to 1 over 10 to the power 4, which is going to be 10 to the power minus 4. Don't really need a calculator for that one, and that will be in seconds. Now 10,000 oscillations per second, one would expect it's a very small time period. If the frequency was used to drive a radio speaker, could it be heard with someone with good hearing? Okay, so for this one here, the answer is yes, because a person, well, the value is actually less than 20 kilohertz. Okay, which is the same as 22 times 10 to the power 4 hertz. A human ear can hear frequencies 20 hertz to 20 kilohertz. Convert 20 kilohertz to hertz. Okay, so really what is the K standing there? So that's actually K is equal to 10 to the power of 3 or 1000, so therefore the answer is 20,000 hertz, or you could actually write it as 2 times 10 to the power 4 hertz. Calculate the periods of 20 hertz and 20 kilohertz. So again, the frequency is equal to 20, so the period is equal to the inverse of the frequency, which is going to be equal to 1 over 20, which equals 0.05 seconds. Now if I do this process again with the 20 kilohertz, which is again 1 over the inverse of the frequency, 1 over 20,000 hertz, and that gives me a value of 5 times 10 to the power minus 5 seconds. A stone is dropped in a still pond, circular waves are produced. It is noticed that the waves spread, the amplitude becomes smaller. So let's say I drop in a little rock, it produces wave fronts and they're going to get larger and larger. However, the energy here is going to be the same as the energy here, however it's over a much greater region. So therefore the amplitude is going to decrease over distance, because the energy is being dissipated. So energy is being dissipated over a greater area. Alright, let's have a look at question number 13 now. So consider the following graph below, calculate the following, the amplitude of the wave. Okay. So what we have here is the displacement, so that's the particles moving up and down, or longitudinal, doesn't actually say in the question here. So for part A, the amplitude, I'd be looking at this point here and taking it back to the y-axis. Okay, So for this one here, I have the amplitude, so that's for part A. The amplitude is going to be equal to 2 centimeters. Calculate the period of the wave. Okay. So the period of the wave is the time taken for one oscillation. So from here to here, and you can actually see the time goes from 0 to 0.2 seconds. So the period of the wave is equal to 0.2 seconds. Part C, what is the frequency of the wave? Just like the previous questions here, frequency is inverse of the period, which is the inverse of 0.2 seconds, which will equal 5 Hertz. A dipper in a ripple tank produces a pulse every 0.2 seconds, and the waves produced have a wavelength of 4 centimeters. Okay, so if I'm going to take the information, so more or less there is a dipper which goes back and forth, up and down, and it makes a splash at a point. So it's going to do that every 0.2 seconds, so it's going to produce one wave, two waves, and the time between these ones here is going to be 0.2 seconds. And you're also told that the wavelength is equal to 4 centimeters. So 4 centimeters, which equals 0.4 meters. Just remember you've got to use the SI units. Find the frequency of the wave. Again, that one's fairly straightforward. So the frequency is the inverse of the period, which is equal to 1 over 0.2, which equals 5 Hertz. What is the speed of the wave? Velocity is equal to frequency times wavelength. So the frequency is 5 Hertz, the wavelength is 0.04 meters. So the velocity is equal to 0.2 meters per second. Now you could have actually done this a different way, because remember velocity is equal to distance over time. So you're actually told the distance here, so 0.04 meters, and the time it takes to cover that distance is 0.2 seconds. And that ends up as still 0.2 meters per second. So there are actually two ways that you could actually have done it. What will happen to the wavelength of water if the frequency of the dipper is increased by a factor of 2? So when it comes to these types of questions, do not substitute values in. It's actually looking at proportionalities. So with part C, the frequency is going up by a factor of 2. What is going to happen to the wavelength? So velocity is equal to frequency times the wavelength. Velocity divided by wavelength is equal to the frequency. So the inverse of the wavelength is proportional to the frequency. So if the frequency doubles, then the wavelength is going to do the inverse. So the wavelength is going to decrease by a factor of 2, which is technically it's going to be halved. Part D, what is the new period of wave? Okay, so what's happened to the frequency? So period is equal to the inverse of the frequency, so if the frequency doubles, the period halves. Now if that's 0.02 seconds, then the period is going to be half of that, which will be 0.01 seconds. Antenna for television must have a size approximately half the wavelength of radio waves that are going to be detected. So this is actually alluding to whatever you work out the answer, you're going to have to halve it. Okay. So television on physics channel 11 transmits with a frequency of 150 megahertz. Calculate the size of the antenna if and you're told that the velocity of radio waves is actually 3 times 10 power 8 meters per second, which is the speed of light. So this is often referred to as c. Using the wave equation, velocity is equal to frequency times the wavelength. That's times by, so on the other side it's divide by. So velocity divided by frequency is equal to wavelength. Now I'm going to substitute my values here. So that's 3 times 10 to the power of 8 divided by the frequency, which is 150, times 10 to the power of 6, because megahertz is equal to a million, or 10 to the power of 6. So then that gives me a wavelength of 2 meters. Now the antenna has to be, and this is just general antenna design, always has to be an even multiple, otherwise you get the resonance and the harmonics don't match up, etc. So it's got to be half of that. So the antenna is going to be half of this value here, so what's half of 2 meters? That's equal to 1 meter. For the wave drawn below, find the following wavelength of the disturbance. Okay, so this one's fairly straightforward. So this is the starting point, it finishes here. So the wavelength of this disturbance is equal to 6 centimeters, or 0.06 meters. It's always good to always convert them to SI units. What is the amplitude of the wave? So we'll just take that across here, being highly technical. So the amplitude, so I'm just going to put amplitude, is going to be equal to 4 millimeters, which is equal to 0.004 millimeters. Given the speed of wave is 100 centimeters per second, so 1 meter per second, because there's 100 centimeters in a meter, find its frequency. Okay, so for part C, change my colors back again. Velocity is equal to frequency times the wavelength. So that's times by, on the other side will be divide by, so frequency divided by wavelength is equal to the frequency. So it's 1 meters per second divided by the wavelength, which was 0.06 meters. That's equal to my frequency, and that is equal to 16.7 hertz. What is the period? So again, what is the time it takes to go from one oscillation? So the period is the inverse of the frequency, so that's 1 over 16.7. However, because we rounded it off, it may mess it up, so it's probably easier just to do it this way here. So just inverse this fraction here, which will be 0.06 over 1, so 0.06 seconds. Alright, give concise description of the following terms, the phase of the wave. Now, as I demonstrated before in class, you can actually think of the wave pattern as actually a circle that rolls around. Okay, so starts at 0, 90, 180 to 70. So if I actually do a wave here, that's my starting angle, so that would be 0 here. That would be 90, where it crosses over, that's 180, and that would be 270, and of course when it finishes that will be 360, or starting the new wave. So the phase of the wave is technically referring to what the starting point is. So this one would actually have, this is a normal sinusoidal curve, but I could actually have another sine wave which would actually look like this. So it's actually starting at this point, which would actually correspond to that point there. See how it's actually going down? So that's actually going down. So this is starting at 180, 270, and then it would actually go back to the middle point, which would be 360, or starting again at 0, and then that would be the next sine wave, just like we've got over here. So that's when we say that this is 180 degrees out of phase. Now the medium is what it actually travels through, so that's where the energy is flowing through. And of course you don't have to have a medium, because electromagnetic waves can actually travel through a vacuum. Now the amplitude corresponds to the energy of the wave, but it can actually, when we're talking about, we have a particle medium, so whether it's a gas, liquid or solid, that would also talk about the displacement of the particles. At a popular surfing beach, physics code, 20 waves are observed to reach the coast in 2 minutes. Find the period of the waves. Okay. So we're going to change this one here into 120 seconds. So 20 waves are going to occur in 120 seconds. Find the period of the wave. Well, technically 20 waves are taking up 120 seconds, so how much is one wave going to take? So I'm simply going to do 120 seconds, split 20 waves for each of the waves, and that is going to equal to 6 seconds per wave, and that is equal to my period. Find the frequency of the waves. Okay, again, period is the inverse of the frequency, so 1 over 6, and that would round off to 1.7 Hertz. Comment on whether you feel this would be a good day for surfing. I would probably say no, not that I'm a surfer, but trying to catch a wave every 6 seconds is going to be fairly choppy and rough, though I could be corrected by an expert. If you had that question in a test, you would just need to put in your reason, and if the reason was logical, then it would be accepted. So you could actually answer yes, provided it had a valid reason. So again, the mark would look at the logic of your answer. Question 25. A stone is dropped into a lake. After 7 seconds, 49 ripples are spread out from the point. Okay, so if a stone is dropped, it's going to produce all these ripples, and there's going to be 49 of them in a span of 7 seconds. So now you're also told that the radius of the outermost ripple is 1.4 meters. So that's the time interval for 49 waves, and you're actually told that so when you add up all the individual waves here in terms of their wavelengths, that's going to equal to 1.4 meters. So the period here is going to be the 7 seconds split 49 waves. So the period is going to be equal to the 7 seconds. So therefore it's 1/7 of a second. Now I'm going to leave it expressed like that for the time being. Find the frequency. So the frequency is equal to the inverse of the period. So the inverse of this one here, 1 over 7, is going to equal to 7 Hertz. Okay, so what is the wavelength? Okay, so the wavelength is going to be, right, I've got 1.4 meters, and that is for 49 waves. So I split that 1.4 meters 49 times, then that will give me a wavelength of 0.02857. Now because I've got 2 sig figures here and 2 sig figures here, I'd need to express that as 2 significant figures, so that would be 0.29 meters, because the 7 rounds up to 5, which makes it a 6, and then that rounds that up on as well. Okay, and that is the end of the assignment. Thank you.